formula, US is equal to pi c square sigma a square over E. So plane stress condition, this is in plane stress condition. Hence, dus over dc, which is equal to 2 pi c sigma a square over E. So here, in this case, energy release from the circular region is given by the formula 1 here as above. So that is taken for this region. Okay. For the body in plane strain condition, thickness in z direction into the plane of the page, E is replaced with E over 1 minus mu square. So US is equals to the strain energy, US is equals to pi c square sigma A over E times 1 minus E over 1 minus mu, that is plane strain condition. As plane strain is more severe on the material, it is better to experiment in the plane strain condition. The surface energy of the crack length 2c and the unit width over depth is fracture surface energy U is equals to 4 gamma fc. And from this, du of gamma over dc is equals to 4 gamma f. This is the difference in the energy between body with crack and one without crack. As pointed out before, the surface energy is the fracture surface energy and not just the surface free energy. The origin of this energy is contributions from the dissipative mechanisms like plastic deformation, micro cracking, and phase transformation, in addition to the energy of the broken bonds. The unit of joule per meter depth of the body is applicable. Note that the Griffiths experiment is easily understood in the displacement controlled mode, that is applying a constant displacement and see what happened to the crack. And it is more difficult to comprehend it in the force control mode by applying constant far field force. In the force control mode, the force do work on the system and hence the energy accounting process is more involved. Therefore, it is better to visualize sigma as arising from far field applied displacement. Okay, so now we have formula for US and the U gamma, which are required. So when we already formulated this, from this we obtain this formula. Okay, so combining these two formulas together, this one dus over dc is this formula, and du gamma over dc is this one, which is given here. So from the two, the left hand side increase linearly with c, while right hand side is constant. Okay, so this one is increase with c. As c increase, as the crack length increase, this will increase, and this one is constant. The equal representation, the bare minimum requirement, the critical condition. That means the minimum crack size, which will propagate with a balance in energy. That is in between the elastic energy release due to crack extension and the penalty in terms of the fracture surface energy. So the critical crack size is calculated from this relation. So C critical, which is equals to crossing this equation, we can find 2E gamma F over pi sigma A square. C is the half crack length. As we know, it is 2C, so it is half crack length. A crack below this critical size will not propagate under the constant stress sigma E. Whether a crack of size greater than or equal to C strike will propagate will depend on the English condition. Begin being satisfied at the crack tip. A sufficient stress concentration should exist. This stress sigma A now become the fracture stress sigma F. Crack of the length C strike will grow unstably if the stress exceeds sigma F. So C strike is equal to 2 times of gamma F over phi sigma F square. That is according to Griff's criteria. This criteria, finally, what you can get this. Crack propagation just starts to pi C sigma A square over E is equal to 4 gamma F. Substituting the strike condition here, finally what we can get is this formula. Okay. So C is equals to 2E gamma F pi sigma F square is the thing which we need critically now. So the Griffiths formula sigma F is equals to radical of 2 gamma E over pi C. For that, at a constant C, that is C is equals to C critical, when sigma exceeds sigma F, then the specimen fails. That means sigma F, the failure stress sigma F is equals to radical of 2 gamma E over pi C 1 minus the Poisson ratio of material mu square. An alternative way of understanding the Griffiths criteria, that is energy-based criteria, is here sigma naught, the far field stress. And once this happens, there is a small crack propagate. Change in energy on the introduction of the crack. Delta U is equal to 4 RF, gamma FC minus pi C square sigma A square over E. This change in energy delta U should be negative with an increase in crack. Look here, d delta U over dc is 0 at this point. Look, it is 0 here. Here it is positive slope. It shows positive slope. And then here it shows a negative slope. Okay, it shows negative slope. In the positive slope region, it is having a stable crack. But in the negative slope region, it has unstable cracks. At the point where d delta U over dc, which is a critical point of critical size of crack, it implies the critical size of crack that is 0. Yeah, so this is the representation for the equations of this thing. So Griffiths versus English criteria. For very sharp cracks, the availability of elastic energy near the crack tip will determine if the crack will grow. On the other hand, if available energy is sufficient, then the sharpness of the crack tip will determine if the crack will grow. Sharp crack is limited by availability of energy, while a blunt crack is limited by stress concentration. So for that, according to Griffiths, sigma F, the fracture stress, which is equals to radical of 2 gamma over pi C critical. And here, sigma f according to English, which is equals to E gamma rho over 4A naught C. If rho is equals to 8A over pi, Griffiths and English criteria give the same result. If gamma is approximately equal to 3 times A naught, Griffiths and English criteria give the same result. They are crossover criteria, that is. So C strike, which is the critical crack length, is equals to 2 gamma E pi sigma F square. And according to English, it is E gamma over 4A naught sigma F square as a whole rho, that is radius or the crack radius. So modern fracture mechanics, stress intensity factor K, material parameter, fracture toughness Kc, energy release rate G, material parameter in this case, critical energy release rate Gc, J integral J, material parameter Jc, crack tip orientation, crack tip opening displacement, which is delta, material parameter delta C. So, so we are going to see another phenomena which is developed by Irwin, another scientist, G.R. Irwin, fracture dynamics. So we are going to see that point. Historically, in the old times, sorry, I'm going to just so now I'm going to see the concept of fracture mechanics. So historically, in 1910 to 20, fracture was studied using English and Griffiths. These are two scientists who begin the fracture mechanics, and they are called fathers of fracture mechanics. Wherein the fracture stress sigma F was calculated either using global or local criteria. So the birth of fracture mechanics is 1990s. About 1990s, more scientists appeared and developed the fracture mechanics to framework to the current state, and lead to the concept of stress intensity factor K, energy release rate G by Irwins and other scientists. This concept worked well in the domain of linear fracture mechanics or linear elastic fracture mechanics for brittle materials. Crack tip stress were characterized by the stress intensity factor. In the presence of crack tip plasticity, some of these concepts were extended if the crack tip plasticity was small or very small scale yielding. In ductile materials, with the large plastic deformation at the crack tip, concept of J integral is evolved, wherein the stress fields ahead of the crack tip are termed as HRR fields, and the J integral characteristic characterize the field intensity of the crack tip. The concept of crack tip opening displacement, CTOD, was also proposed to characterize the cracks in ductile material. So, concept of energy release rate, or G. G is defined as the total potential energy, pi, decreasing during unit crack extension. That DC means